September 3rd, 2017. This is supposed to be the week 2 Wednesday stream that never went off because Twitch went down for the whole night. So we're making it up now. What I wanted to cover on Wednesday night was the topic of vectors. It's something that we learned last year in our intro physics classes, and we're going to see as we go through our static effects that it's going to have more and more use looking at these types of quantities. But I'd also like to talk a little bit about some intro calculus ideas. I know a bulk of our class is in calculus this year, but maybe you need a little bit of a refresher, or maybe you want to see it kind of in more of a physical way, because a lot of the calc classes deal with kind of like abstract ideas, or they don't really put them to an application. I'd like to talk a little bit about some intro calculus stuff, because we're going to be seeing it in the coming weeks in class. So starting off with vectors, that's going to be our first topic. Our second topic is going to be the calc there. Okay. Looking at vectors here, one of the things to remember about vectors is that, here's a little axes, they're really representing some quantity that has both a magnitude, that is a size, and a direction as given by the arrow. And one of the main things we learned last year was if you wanted to add or subtract a vector, you needed to use the head-tail method. As my handwriting looks like a 4-year-old. And this head-tail method is saying that if I have some vector A here in green, and I wanted to add it to some vector B here in blue, then I can't actually put them together via the tails like this. I need to shift the vectors. And there's a common idea known as the parallelogram idea, where I can either shift B up like this. Note it has the same size down here. It's just shifted up and it has the same direction. So that would be B. Now they're connected head tail. Or I could shift A across, making sure I don't rotate it. And whenever I plot that vector, we'll see that A has the same length, same direction, and I have this nice parallelogram there. The reason we did this was so that we can go from our starting point here to a finishing point out here, because that vector, that is the resultant R, and that is actually the vector we care about. Now in this case here, we're kind of moving in generalized spatial coordinates, so we weren't moving at right angles to each other, and that poses to be a slight bit of an issue if we want to do things on our calculators or just like working out numbers. This way works perfect if we can just measure this and have a scale that we've set up, and we did that last year. But if we actually want to get calculations like we've done in class the past 2 days with our electrostatics, then what we may have to do is we may have to break up this vector A initially into vector components, because if I wanted to add vector A and B together, other than graphing at the moment, I really don't have a good way of doing that. So what we can do for vector A and for vector B is, well, not so much for B, is we can look at whether or not these vectors are on our x and y axis. And if I look at B here, it's fully in the x direction, so it's fine. Vector A, on the other hand, it's not. It's moving into the first quadrant in the xy plane up at about a 45-degree angle. So we need to split some stuff here. If we know an angle for this vector, and let's just give it some angle theta for lack of argument, or maybe we had some other angle up here, we can call that phi, just because, why not? Then what we would need to do is we need to split A up into its horizontal component and its vertical component. Because when we split something up into the horizontal and vertical components, we can sum up those x components of the vectors, and then we can sum the y components of the vectors, whatever they are. So if we were looking at the x's here, we could sum up ax and then b in general, because b is only in the x direction, and in our y direction we would only have a y. So by splitting a vector into its x and y components, we can actually start adding them together, kind of like a number line did. Because if you think back to your elementary school days, where you had a number line, you know, starting at 0, 1, 2, 3, -1, -2, -3. whenever you're adding like 1 plus 2, what you were truly adding, if you think about it, was 1 plus 2. And then that gave you some resultant of 3. And this is actually the head-tail method. So this is what we're trying to do. We're trying to put everything back on some sort of number line so we can add them up easier. And then since they will be at right angles to each other, we can do simple mathematical operations such as Pythagorean's theorem and whatnot. If you're trying to think back, like, how do I break this up? Then we should think back to our great chief SOHCAHTOA. If this is vector A and we're using SOHCAHTOA, this is super important. Okay, if you don't remember the great chief SOHCAHTOA, you need to remember the great chief SOHCAHTOA. He's your best friend. Because that idea of SOHCAHTOA will allow us, and let's just take a look at this for our orange theta here. It allows us to break up this vector into 2 parts. What I'm trying to do is I'm trying to find the x component here, and I'm trying to find the y component here. And since we know we're on an axis, and this is the x and this is the y component, then by definition, this must be a right triangle. It has to be. There's no way around that. And note, once again, this is like a head-tail, because look, this x direction and this y direction gives us the vector itself. So what we can do here is we can label all of our parts of the triangle. From the angle cutting across, we see that this is the opposite side. This side here is next to the angle, so is this side here. But this side here is a perfect name. It's the hypotenuse, so we'll call it that. And then this leaves us just one other side. It is the adjacent edge, because we've already named out the hypotenuse. With this, we can say that the sine of this angle theta, whatever it is always equal to the opposite side over the hypotenuse. We can say that the cosine of angle theta is equal to the adjacent side over the hypotenuse. And last but not least, we've got tangent of theta equals the opposite over the adjacent. Okay. Now, if you're in your math classes, you know, we can do like 1 over sine and 1 over cosine, 1 over tangent, the cotangent functions. But these are like the primary ones right there that we're kind of playing with. Remember, there are also inverse functions to each of these, such as inverse sine, inverse cosine, inverse tangent, and those are set up to find theta. So if you knew your opposite and hypotenuse side, but you didn't know what theta was, like this right here is the big question mark, like, I don't know, what is that? Then you could find it if you knew your sides. Most of the times we'll know theta and we're looking for sines off of it, but the same idea still stands. But once you're able to find AX and AY, then you could run up and add them, and now you have those given components. What that allows you to do is, especially for our electrostatic stuff, is now that I have some new vector down here, we'll call it AX plus B, but really it's just like the sum of the x direction. And since we also have some vector here, this was AY, but remember it is really just the sum of all the vectors in the y direction, we can add these together. Now note, once again, just like we saw up top, that is tail, tail, and we don't want that. So we'll either have to shift A over, or the sum of the y directions over, or the sum of the x directions up. So when I do that, that could go up there, or this could go across like that. In the end though, it still does give me some start to finish, which is that. And since I know this is all in the y and all in the x direction, I know that is a right angle, I know that is a right angle, and the only thing I have to do here is a Pythagorean theorem on that. Okay? So you can Pythagorean theorem, you can find that quantity, you can use your inverse functions to find any weird angles you'd like. Remember, angles are always starting from the positive x-axis and working their way around, even if they have to go way, way, way around to get that, because this is the positive direction, and if you wanted to, you could go in this direction, which is the negative direction of theta. That's just a convention we have in math class. Okay, so that's kind of like a quick primer. I know we've done this in class a few times now, but if you wanted to see it, wanted to get more practice or a general idea again, it is sitting here. Okay. Okay, that's the stuff we should remember. Now the stuff we might remember if we've done it before. Calc time. Okay. What happened there? If you took calculus last year, this should hopefully seem familiar. Maybe give you more of an intuition on items. If you haven't taken it, then just trust that what I'm going to say is true, or is true enough as it can be. Okay. I like to start with this idea of calculus as we're getting closer into the fall here with pumpkin rolls. Okay, so let's imagine for a second I have a tasty pumpkin roll. I just draw my pumpkin rolls as logs. Okay, now this pumpkin roll, it has some length here, L. It's just however long I made the pumpkin roll. Did I make it a foot long, 20 feet long, a mile long pumpkin roll? Greatest pumpkin roll in the world. Okay. Now the issue is, and if you don't believe me, we'll just suspend disbelief for a second, is that maybe I've got a lot of friends sitting around. Maybe I've just got one friend, and if I had just one friend, I could slice this pumpkin roll in half. I could give them half of the pumpkin roll, and I could take half the pumpkin roll and be like, we're all full. If I had more friends, I could slice this pumpkin roll into further sections. So we're each getting like a fourth of the pumpkin roll now, okay? But the issue is, what if everybody is my friend? And what if there are an infinite number of everybody's? Like, what if there's an infinite number of people just sitting out in the universe, and I invite them all to my house, and we don't create a black hole, and everybody gets the pumpkin roll? But I only have so much pumpkin roll. Well, what will end up happening is I'll end up cutting that pumpkin roll thinner and thinner and thinner. It'll keep getting smaller. There's nothing we can do about that. And when it keeps getting smaller, you'll eventually get just a sliver of pumpkin roll. It'll be like basically transparent. And you'll be like, wow, that's the thinnest pumpkin roll slice I've ever gotten. But then more friends will show up, and I'll have to take that sliver and cut it again, because I've got magic, physics, calculus powers, and I can cut even the thinnest slice of pumpkin roll as thin as it ever needs to be. So I keep cutting these infinitesimally thin pumpkin roll slices even thinner, and they keep getting thinner, and they keep getting thinner. Kramer would be so proud of me from Seinfeld. He wishes he had a meat slicer this thin. But we keep getting these like super thin slices of pumpkin roll. And eventually everybody's gotten these pumpkin rolls, and if we wanted to, we could bring all of the pumpkin rolls back together, set them side by side, and we'd still have the full pumpkin roll. We've just cut them very thin. Okay? So that's the idea of what we're doing with this pumpkin roll. We're cutting it thin. Now when we're cutting it thin like this, each slice of pumpkin roll is actually representing a tiny bit of length of the pumpkin roll. And this infinitesimal bit of length, we will simply call this DL. It's some fractional piece of the length. It's super thin. It's super infinitesimal in nature. So it's just a tiny fraction of the whole, okay? Anytime we see this D here, that is what is being represented. It is a tiny fraction, an instant of that pumpkin roll slice, okay? So that's what we're looking at there. Now, whenever I described putting the pumpkin roll back together, we were adding up all of the pieces of the pumpkin roll, just like the idea of if I had two half pieces of the pumpkin roll, L over 2, and then another half piece of the pumpkin roll, I could say L over 2 plus L over 2 equals L. That's the full pumpkin roll. Writing that out, though, if I had an infinite number of pieces, would be insane. So thanks to some clever mathematicians, we got Newton pretty much on the forefront of this, we have created something known as an integral. An integral, all it is a fancy summation. If you remember last year when we talked about summations, this is just adding everything together. And even if you were watching this video from the start, you saw up here, hey look, I said the summation of everything in the x direction, which is the addition, or the summation of everything in the y direction, which in this case was just 1, existed. So we've used this summation idea before. It's just adding everything up. If you only have 2 things, that's all it is. If you've got 8 things, you're going to have more addition signs. If you've got 1,000 things, your hand's going to get tired. So we've gotten a faster way to do it, this integrand right here. And basically what it does is if I integrate all of the tiny pieces, dl, of my pie, okay? So give me all of the pieces of the pie, or the pumpkin roll, every infinitesimal slice. We're going to add them together, okay? And we're going to do it from, if we measure the pumpkin roll, the side that is 0 length, and then if we imagine that all of these were kind of in order, we're going to go all the way over until that pumpkin roll reaches length L. And the way we'll put this on our integrand is starting at our point 0, that's this initial point, and then ending at some final point L. Okay? Now, since we're only trying to add up all of the little pieces here, we know what this answer has to be. If we're just adding up all of the pieces, then if I put all the pieces back together, I know this is going to have to equal L. More technically what it equals is it equals L from our boundary. And these are our boundaries right here. We know that these are like the edges of the pumpkin roll, the leftmost edge, the rightmost edge. Those are the bounds. So an upper and a lower bounds. So what we do here, and it's just common to write this in mathematics with kind of a line, is we're going to say, look, we have some length L here, and it goes from the upper bound to lower bound. And what that means is we'll take our upper bound minus the lower bound while we put in these values for L. So when I put L in for L, kind of semantics there, I get L. When I put in 0 for L, I get 0. Well, L minus 0 equals L. Hey, look, we have the length of the pumpkin roll again. Way to go. If we wanted to kind of change how our boundaries look, maybe I only want to get half of the pumpkin roll back from everybody, so I can take an integrand from 0 to L over 2 of dl. If I did that, I'm going to integrate this. It's just going to move up to L. I'm going to have my boundaries, which go from 0 to L over 2. And when I put in my quantities, I'm going to get the upper L over 2 minus the lower. And hey, look, I've got back half of a pumpkin roll. This also would work if you did it instead as from L over 2 to L, like the second half of a pumpkin roll of all the infinitesimal slices, because that would give you L from L to L over 2. And when we put those quantities in, we'd get L minus L over 2, which is L over 2. So look at that. We once again found half of our pumpkin roll. That's not crazy at all. Okay? So that's what we're doing here in terms of integral calculus. We're just adding everything together. Okay? We're just adding everything together. It's nothing crazy there. And that is going to be the bulk of what we do this year in the physics class, which is integral calculus, the idea of adding quantities up. Okay? If you've never seen calc before, maybe you're in calc A, maybe you're in pre-calc, we will talk about how to integrate different quantities other than just having the infinitesimal pieces here. Nothing gets too crazy in physics class. Normally we have polynomials that we integrate, so if you've done integration before, we're not going to have any trigonometric substitution. I doubt we'll have anything by parts. A lot of it will be, here's a polynomial that you're integrating. Maybe you're integrating sine and cosine. If you're like, what, Mr. Botzer? We'll come back to that later on in the year. Don't you worry, we'll have more videos. Okay? So this is some intro calculus, and if you want, make me a pumpkin roll. Bring it into class. We'll cut it up as small as we can, and we'll eat it. So Okay. Have a great Labor Day weekend. If you need any help with any of this stuff, or you're confused even further, just come and see me. I won't leave anybody behind. We'll get all this stuff. This is mainly useful for the AP Physics C. Okay. So if you're planning on taking the AP Physics C stuff, you need this. If you're like, Bots, I don't want to see this. I'm not doing that in college. I'm a business major. Don't worry about it. Do your best. We'll get there when we get there. Okay? Okay. Take it easy, everybody. These videos will be on this page, the Twitch channel, for a month, and then they'll be up on the YouTube forever. Bye.